Okay, gang, this should be the last in this little installment of videos on waves. In Chapter 12, we finished talking up recently about how the wave equation is velocity is wavelength times our frequency. And if we look at where each of those come from, frequency comes from the transducer, right? So that's more of a manufacturer. Comes from the source, right? Which is the manufacturer, which is our transducer. How do we know? We look on the side, it has a number. That number should also line up with the number that shows up on your screen when it's plugged in. All right, velocity comes from the medium. And since we're in soft tissue, that is going to be a 1540 meters per second. We saw in the last video that is mainly due to the stiffness level of soft tissue. Okay, if we look at now on page 31, that table 5, it talks about propagation velocities in the body. It's slow on the top to fast on the bottom. We want to get in mind or sort of memorize a few of these. All right, the main one is going to be the slowest, which is air, which is somewhere around 330 meters per second. Depends on temperature, but 330-ish, 340-ish. We get into soft tissue. That's at 1540 meters per second. Again, that means it'll go 100 or 1,540 meters every Mississippi. And on the high end, we want to see that there is bone, which is in the 4,000 range. Okay, 4,080. But if you remember those as the slow end, the fast end, and then the majority, which is right in the middle of soft tissue, we can sort of label the other ones. Water is going to fall a little bit in the middle, right, between air and soft tissue, closer to what we are 1540, but it's almost at 1495, I guess it shows there. Okay, all the organs, a little more denser organs like liver, kidney, muscle, right, are going to be rightly above that. But if we take the middle few there and blend them together or average them, we come up with this 1540. So that's where we stay with that. Again, depends on the stiffness. That can be measured by the bulk modulus. If you're a big engineer, that's the big fancy term that engineers use. Otherwise, we think of stiffness, high stiffness, low density. That's bone, right? Bone is very stiff, has a low density. Once you dry it out, they're very light, but it has a lot of stiffness, strength to it. So that's why this one is at the higher end. Air, obviously not very stiff. We can move that around. Okay, so that takes care of the velocity and it takes care of the frequency. What about the wavelength? The wavelength depends on both, right? You pick up a transducer, it tells you what the frequency is. We know we're in soft tissue, so we know the velocity. So wavelength will depend on what the velocity is divided by what frequency we are using. So it's sort of like the third child, right? Get the first two, get what they want. Third one gets whatever is left over. Okay, so it depends on that. We have to adjust the velocity or the frequency to get adjustment there. All right, so moving on there in Chapter 2, what else is there to things to talk about? Why do we care about the wavelength? Well, since it comes from frequency, we'll see later that if we have a lower frequency, the positive is we get depth. We get a lot of penetration. The downside is we get no really good resolution to see small stuff. If we go on the other end and we use a higher frequency, and this is stuff we're going to hear lots of times, the positive is we get great resolution. The problem is we don't get a lot of depth, a lot of distance. That's why coming down the street, I think I've told you, you hear somebody's car and you hear boom, 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 boom. You hear the low frequencies because they can travel far, but you don't get the high frequencies because they don't. Okay, so that gets into that, and I've gone too much, so we're going to add one more video just to try to finish up Chapter 2, so Monday in class we can go completely through 2 and answer questions. So hang on, we'll do one more, and we'll be done for the day.